So friends, in my previous video, I was discussing about the symmetry elements. We have discussed identity operations followed by center of symmetry I, and third one, that is rotation axis. Now in this video, we shall discuss about rotation axis. So in rotation axis, which is symbolized by Cn, when n is equal to 2, that is 180 degree rotations. After 180 degree rotations, if we'll get equivalent structure, then the molecule have the rotation axis, which is symbolized by C2. If the molecule have rotation axis, if on this rotation axis, if I can perform cyclic rotations at around 120 degree rotations, after 120 degree rotations, if I'll get the equivalent structure, then the molecule have the rotation axis, which is symbolized by C3. Same way, 90 degree rotations, after 90 degree rotations, if I get the equivalent structure, then molecule have the rotation axis at C4, then C6, C5, and sometimes infinite is also present in linear molecule, where the infinite degree of rotations, after infinite degree of rotations, will get the equivalent structure. Therefore, the molecule have C infinite. Now, this is the square planar molecule, like BTCl4 molecule, NiCN4, 2- compounds, where these square planar molecules, which consist of number of rotation axis. Now, number of rotation axis, that means in this molecule, the one imaginary axis passing through the center of that molecule, and if I can rotate at 90 degree rotations, after 90 degree rotations, I'll get the equivalent structure. So that is considered as C4, along with 4 C2s are also present. Okay, so 1, 2, 3, and 4. 4 other C2s are also present. So this molecule or compound has number of rotation axis. So which one is considered to be a principal axis? Therefore, we can say that those axes which has n value higher. So here C4, but necessarily C4, n is equal to 4, and these all subsidiary axes have n is equal to 2. Therefore, C4 is considered as principal axis, highest order. So those rotation axis which has highest order rotations, that which is considered to be a principal axis. This is the benzene molecule, where C6. So after 60 degree rotations, the molecule give the equivalent structure. Therefore, this rotation axis is considered as C6, which is passing through the center of that molecule, benzene molecule. And other 6 C2s are also there. 1, 2, 3, 4, 5, and 6. Now next one is plane. The next symmetry elements, that is called mirror plane. What is mirror plane? Now mirror plane, that is an imaginary plane within that molecule, which divides it into the two parts, and these both the parts which are mirror images of each other. Look at this example, human body. Now if a plane is passing through the center of that body, and it divides into two parts, this part and this part, both this part which are mirror images of each other, that is called mirror plane. So the definition, another definition of mirror plane, if a reflection is carried out over the plane of symmetry and the new positions of atoms are noted. Okay. So both these parts which are mirror images of each other, therefore this human body has mirror plane. Same way, this pencil, if you put a mirror plane like that, it divides into two parts, this part and this part, both this part which are mirror images of each other. Therefore, this molecule have mirror plane. So human body has an approximate sigma operations. Linear objects have infinite sigma. Now look at this linear molecule. This is linear molecule. If I put one plane over here, if I can put second plane over here, third plane here. So infinite number of planes, if I can put infinite number of planes, through which it divides into two parts, and both these parts which are mirror images of each other. Therefore, linear molecules have infinite number of mirror planes. Now, mirror planes, there are three types of mirror planes. Which one? Look at this. The first mirror plane, that is called sigma V. Now, V stands for vertical. So, vertical plane. H, second plane, that is called horizontal plane. That is called horizontal plane, sigma H. And third one, that is called sigma D. D stands for diagonal plane. So there are three types of mirror plane: sigma V, sigma H, and sigma D. Sigma V, sigma H, and third plane, that is called sigma D. Now, sigma V, simply I can say that that is the plane which is parallel to the principal axis, or in absence of principal axis, it is parallel to the rotation axis. So which plane, mirror plane, which is considered as sigma V? So simply I can say that the plane which is parallel to the principal axis, or in some of the molecules where only one rotation axis are present, then we can say that it is parallel to the rotation axis. So that is called sigma V. Now sigma H. Now this is the mirror plane which is perpendicular to the principal axis, or in absence of principal axis, which is perpendicular to the rotation axis. Okay. So one plane, sigma V, which is parallel to principal axis, or in absence of principal axis, we consider as rotation axis, parallel to the rotation axis. Sigma H, the mirror plane which is perpendicular to the principal axis, or in absence of principal axis, which is perpendicular to the rotation axis. Third mirror plane, that is sigma D. Now, this is a typical plane. Look at this. The plane which is parallel to the principal axis and also passing through the angle between two subsidiary C2 axis. I will explain later on about sigma D. So we shall discuss one by one these mirror planes: sigma V, sigma H, and sigma D. The first plane, that is vertical plane. Now this is the structure of water molecule. This is oxygen and these are the two hydrogen, and it has bent-like structure. Now if I can pass this plane, passing through the oxygen atom, and it divides into two parts. Now this part and this part, which are mirror images of each other. Okay. Therefore, and this is parallel to the rotation axis. Now, where is the rotation axis? So rotation axis, it passing through the center. Okay. So this is parallel to the rotation axis, and it divides into two parts. One part and the other parts, both these parts which are mirror images of each other. Therefore, this is called sigma V. Another sigma V, look at this. So this plane, if I can pass this plane, so that all these three atoms, they are situated into the plane, and it cuts the or divides the molecule into two parts. in such a way that both these parts which are mirror images of each other. So this is also considered as sigma V. So molecule have two types of sigma V. So H2O having 2 sigma V. And this plane which is also parallel to the rotation axis. This is parallel to the rotation axis. Therefore, this plane is considered as sigma V. Look at this very clear structure, which will give you idea about where sigma V planes are present. This is first sigma V, and when sorry. This is first sigma V, which divides the molecule into two parts, and both these parts which are mirror images of each other. And the pink plane which cuts the molecule in such a way that both the parts which are mirror images of each other. So this is second sigma V. So water molecule which has a band structure, it consists of 2 sigma V planes. So clear? Now next. The same way sigma V, now we shall discuss about sigma H. Sigma H, which is considered as horizontal plane. Horizontal plane, that means it is perpendicular to the rotation axis or principal axis. So here, in this molecule, while if we pass an imaginary axis passing through the center of that molecule, this is C4. Okay. This is called as C4. And this green color plane, which is perpendicular to this rotation axis or principal axis, therefore this plane is called as horizontal plane, and it divides into equal parts. Okay. Now here another example, FeCO5 molecule. This FeCO5 trigonal bipyramidal shape, where this is an imaginary axis or rotation axis, C3. This is C3. Now this dotted line or dotted plane which indicates sigma H. So it divides the molecule into two parts, and both the parts which are mirror images of each other. Therefore, this is called sigma H. So sigma H generally which is perpendicular to the principal axis, or in absence of principal axis, which is considered to be a rotation axis. Okay, now the important one, that is dihedral plane. Sigma V and sigma H, which are considered to be easy. However, dihedral plane, they are little bit typical. Now look at this. These two axes. What is the definition of sigma D? Sigma D is a plane passing through the center of that molecule. Okay, along with it passing through the angle between two subsidiary axes. So those molecules which has subsidiary axes are present, where there may be a chances of sigma D. Okay, so here this is a square planar molecule. The square planar molecule which consists of a number of rotation axes, principal axis and subsidiary axis. So these are the C2 axes. So one C2, this is one C2. If I can rotate this C2 at around 180-degree rotations, this fluorine and this fluorine interchange their positions. So this is considered as C2, and this is second C2. Now sigma D is nothing but this is a plane passing through the center of that molecule, okay, and it divides the molecule into two parts. Both these parts which are mirror image of each other, along with it passing through the angle between two subsidiary C2. So this is one sigma d, and this is another sigma d display. This is second sigma d. Now next one, there is rotation reflection axis or improper rotations. So actually there are 5 symmetry elements we have discussed earlier. Identity operations followed by center of symmetry I, then rotation axis, then next one mirror plane, and finally the fifth one, that is called rotation reflection axis or improper rotations, which is symbolized by Sn. Now, rotation reflection axis, that means it would involve the two operations simultaneously. Rotation by an axis, followed by reflection through a plane which is perpendicular to that rotation axis. So look at this. This is CH4 molecule. Now CH4, it has a tetrahedral shape. Now in this tetrahedral shape, if a line, imaginary axis passing through the center of that molecule, and if I can rotate, sorry, this is an imaginary axis passing through the center of that molecule, and if I can rotate at around, 90-degree rotations. So 90-degree rotations, this H1 comes over here, this H2 comes over here. So all these H1, H2, H3, H4, they interchange their positions. Now this structure is not an equivalent structure. The second operation, that is reflection through a mirror plane. This is the mirror plane. So if I can put this mirror plane like that, and it is perpendicular to that rotation axis. So this plane is called sigma h. So these operations, that would involve the two operations: rotation by an axis followed by reflection through a plane which is perpendicular to that rotation axis. So after carrying out this reflection, so what will happen? This H3, their mirror image is here. This H2 mirror image is here. This H1 mirror image is here. And this H4 mirror image is here. So look at this structure. Now the final structure, now you compare with the original structure. This structure, where previously instead of H3, here H1 is there. Instead of H4, here in the original structure H2 is present. Here H2, in the original structure H3 is present. And here H4, here H4 is there. Now it becomes H1. So this structure, which is equivalent to this structure. Therefore, we can say that after performing rotation followed by reflection through a plane which is perpendicular to that rotation axis, and we'll get the new structure, this new structure which has equivalent structure or equivalent to the original structure. Therefore, we can say that this is rotation reflection axis. So generally, rotation reflection axis, it would involve two operations. First, rotation by an axis followed by reflection through a plane. After performing these two operations, if we'll get the equivalent structure, then the molecule have rotation reflection axis. ये जो structure है, ये original structure जैसा ही है. Therefore, we can say that this is equivalent structure. So this is called as rotation reflection axis. So it might be get clear. So rotation reflection axis, it would involve the two operations, rotation followed by reflection. Okay. Yes, look at this. Rotation by an axis followed by reflection through a plane. And after performing these two operations, we'll get the equivalent structure. Now, the important thing, that is a point group. How to derive point group of a molecule? Now, first of all, what do you mean by point group? Now, point group is a shorthand notation. It gives an information about the number of symmetric operations which are possible in a molecule. Okay. Or we can say that point group is a set of symmetric operations. So in a particular molecule, how many number of individual symmetric operations are present? The summation of all these symmetric operations, that is called point group. Now, how to derive point group of a molecule? Look at this example. First example, this is a molecule CHFClBr. This is the structure, okay, geometrical structure of this molecule, where all these N, like hydrogen, fluorine, chlorine, and bromine. So these are some heteroatoms surrounding that carbon. So is there any symmetric operations are present or symmetry elements are present? Look at this. So it would consist of only one cyclic operations, or we can say that only it would consist of only identity. So E is present. Now E is nothing but, if I can rotate at around 360. So after 360-degree rotations, the structure will remain as it is. That is called identity operations. So identity operations, that means no change is made in the molecule. So this molecule has either identity operations, E is present, or we can say that it is symbolized by C1. So the point group of this molecule is C1. The rest of the symmetry elements, like center of symmetry or rotation axis or a mirror plane, or in case of improper rotations, all these symmetry operations are absent. This molecule consists of only identity operations. Therefore, their point group is C1. This is asymmetrical molecule where only identity is present. Therefore, this molecule have point group C1. Now look at this, the second molecule, CH2 double bond C ClBr. Now on this side, the C's positions, there are two hydrogen. On this other side, there are chlorine and bromine. Now, if I can draw imaginary axis. Now, if I can rotate this imaginary axis at around 180 degree. So after 180 degree rotations, should I get equivalent structure? No, because after 180 degree rotations, this chlorine and bromine interchange their positions, but this structure is not an equivalent structure. Therefore, this molecule has rotation axis is absent. if I put the rotation axis over here, and if I can rotate at around 180-degree rotations or any degree of rotations, will not get the equivalent structure. Therefore, this is also absent. On y-axis, if I can rotate this y-axis at around 180-degree rotations, after 180-degree rotations will not get the equivalent structure. Therefore, this molecule has rotation axis is absent. As I told you earlier, every molecule, whether it is a asymmetrical or symmetrical, identity is always present. So every molecule has its own identity. So this molecule has identity E is present. Identity E is present. And identity E is present, and the second element that is if I can put mirror plane like that, which divides the molecule into two parts, and both these parts which are mirror images of each other. Therefore, this molecule has mirror plane that is called sigma. So sigma is present. Sigma is present. So this molecule has only one mirror plane, sigma, and identity operations. Therefore, such molecule and rest of the symmetry elements like center of symmetry, rotation axis, as well as improper rotations, they are all absent. And this molecule has only one mirror plane, sigma is present, and other identity is present. Identity E is present, therefore the molecule has symmetry point group, that is CS. So when the mirror plane is present, which is symbolized by S, so CS, the point group is CS. Now third example, this is the stagger configurations. This is the stagger configurations of this molecule. This molecule has only identity is present, along with center of symmetry I is also present. Look at this. So if I started my journey from this bromine atom through the center, on the other side of the center at the same distance, if I can find the same bromine on the other side, then the molecule have center of symmetry I. If I can start my journey from this hydrogen atom through the center of this molecule, on the other side of the center at the same distance, if I can find the same atom, hydrogen, then the molecule have center of symmetry I is present. If I can start my journey from this chlorine atom to the centers, on the other side of the centers, if I can find the same atom, that is chlorine, then the molecule have center of symmetry I is present. So this molecule has center of symmetry I is present and identity is present. The rest of the symmetry elements are absent, that is rotation axis and improper rotations, mirror planes are absent. Therefore, the point group of this molecule is CI. CI, because inversion center is present. Okay. Look at some of the other examples. Now HCl, which has a linear structure. Now this linear structure, one end having hydrogen, other end having chlorine. Now we can find out the point group of this molecule. So starting with identity. So HCl has its own identity. So E is present. Plus, now we shall check center of symmetry I is present or not. So if I can start my journey from this hydrogen through the center, on the other side of center, there is a chlorine atom. There is no hydrogen atom. Therefore, center of symmetry I is absent. Center of symmetry I is absent. Okay. Now, rotation axis. Now, rotation axis, if an imaginary axis passing through the center of that molecule. Now, if I can rotate, if I can rotate if I can rotate 1 degree rotations. So after 1 degree rotations, the position of these hydrogen and chlorine, they are remain as it is. Therefore, we can say that this is equivalent structure. If I can rotate at 20 degree, after 20 degree rotations on x-axis, the positions remain as it is. Therefore, this is also considered as equivalent structure. After 45 degree, the positions of hydrogen and chlorine will remain as it is. Therefore, which is also equivalent structure. Therefore, we can say that this is rotation axis. If I can rotate at 80 degree, after 80 degree, the position of hydrogen and chlorine remain as it is because hydrogen and chlorine, they are situated into the axis. Therefore, at any degree of rotations on x-axis, will get the equivalent structure. Therefore, this rotation axis, which is considered as C infinite, because at infinite degree of rotations, at any degree of rotations will get the equivalent structure. So therefore, this molecule has C infinite. This molecule has C infinite. This is my rotation axis. This is my rotation axis. And if I can rotate at any degree, suppose if I can rotate at 1 degree, we'll get the same structure. If I can rotate at 20 degree, we'll get the same structure. If I can rotate at 60 degree, we'll get the same structure. If I can rotate 90 degree, we'll get the same structure. So these rotation axis, which is present on x-axis, these x-axis, which is considered as C infinite. So if I can rotate at infinite degree of rotations, we'll get the equivalent structure. Therefore, linear molecules, specifically linear molecules, have C infinite is present. Now, if I can draw a line passing through the center of that molecule, and now if I perform the cyclic operations, on z-axis, now should I get the, or will I get the equivalent structure? No, because both the ends, one end having hydrogen, other end having chlorine. So we will not get the equivalent structure. Therefore, this axis is absent. Same way on y-axis, if I perform the cyclic operations, will I get the equivalent structure? No. So on y-axis will not get the equivalent structure. Therefore, this is not considered as a rotation axis. So only the rotation axis which is present on x-axis, and it is considered as rotation axis. So which is symbolized by C infinite. So at any particular degree of rotations will get the equivalent structure. Therefore, this is called C infinite. Is there any other operations are present? Or is there any other symmetry elements are present? Now we'll check the mirror plane. So whether the mirror plane is present or not. So if I can pass a mirror plane which is parallel to the rotation axis, which is situated on x-axis, and it divides the molecule into two parts, both the parts which are mirror image of each other. Therefore, this plane is called as sigma V. So this is called sigma V. So this plane yes. Now this plane which is passing through the molecule and it divides the molecule into two parts, along with this plane is parallel to the rotation axis. Therefore this plane is called as sigma v. Okay. So this sigma v, so these molecules are linear with the infinite number of rotations and infinite number of reflection plane. So if I put this plane in any angle, we'll get the equivalent structure. Therefore this plane is called infinite sigma v. So the point group of this molecule is, the molecule has E is present plus C infinite is present, which is situated on x-axis, plus infinite number of sigma v planes are also present. Therefore, the point group is E plus C infinite, that is called C infinite. C infinite plus infinite sigma v, therefore it is called as C infinite v. So the point group of this molecule is C infinite v. So infinite, which is present only in the linear molecule. Now the second example, that is called the carbon dioxide. Now this carbon dioxide, starting with identity, first we'll check identity. So identity E is present, identity is E is present, followed by rotation axis. Now we shall check the rotation axis. Now if we draw a line, 1 minute. If we draw a line, imaginary axis passing through the center of that molecule, which is situated on the x-axis, and if I can rotate this imaginary axis at any degree of rotations, we'll get the equivalent structure. So therefore, this is called C infinite. This is called C infinite. Now, is there any other subsidiary axes are present? Look at this. If I can pass imaginary axis passing through the center of that molecule and which is situated on the z-axis, and if I can rotate at 180 degree rotations, after 180 degree rotations, what will happen? This oxygen comes over here and this oxygen comes over here. So they interchange their positions, but the structure is considered to be an equivalent structure. Therefore, this is considered as C2. So C2, which is situated on z-axis. Same way, look at this. This C2 passing through the center of that molecule, and if I can rotate at 180 degree rotations, so after 180 degree rotations, we'll get the equivalent structure. So this is called C2Y. This is called C2Y. C2Y. So which one is considered now? There are a number of rotation axes are present. C infinite, which is situated on x-axis, C2, which is situated on z-axis, and another C2, which is situated on y-axis. So which one is considered to be an principal axis? Now those axes which has n value is higher or higher fold axis. So C infinite, but naturally C infinite which is considered as principal axis. C infinite which is considered as principal axis, and 2 C2 axis which is perpendicular to the principal axis, they are considered as subsidiary axis. That is C2x and C2y, right? So in that molecule, E is present plus C infinite is present plus C2 is also present. The point group is, we can say that this is D infinite. Okay. Along with another that is vertical plane are also present. Look at this vertical plane. This is vertical plane. So if I can put the vertical plane on x-axis and at any degree, this plane which divides the molecule into two halves, and both these halves which are mirror images of each other. Therefore, infinite number of sigma v planes are also present. So along with this, infinite number of sigma v planes are also present, and infinite number of sigma v planes are also present, plus sorry, plus one more plane is present, that is sigma h. This is sigma h, which is perpendicular to that principal axis. So how many number of symmetry elements are present in this molecule? That is, I will repeat, identity E is present, followed by C infinite is present, which is situated on the x-axis, plus two subsidiary C2s are present, one which is situated on the z-axis and another which is situated on the y-axis. So two subsidiary C2s are present. Therefore, E plus C infinite plus 2C2 gives D infinite, plus infinite number of sigma v planes are also present. Therefore, infinite number of sigma v planes are also present, and finally sigma h, which is perpendicular to that principal axis. So sigma h is also present. So plus sigma h, therefore point group is D infinite h. D infinite h. So for a linear molecule where both the ends having the same atoms, where the point group of that molecule is D infinite h. D infinite h. Okay. Now these are the some other example where CH4 molecule. Now CH4 molecule which has tetrahedral point group. Now tetrahedral point group where number of symmetry operations are present. Number of symmetry operations are present that we shall discuss later on: tetrahedral, octahedral, and icosahedral. So these are the three polyhedric molecules where the point group, we have to remember this: tetrahedral, octahedral, and icosahedral. So CH4 molecule where number of symmetric operations are present that we shall discuss later on. Okay. Now, how to derive the point group? Look at this. Now, molecule, if it has a linear shape, and center of symmetry I is also present, then the point group is D infinite H. If the molecule is linear, but center of symmetry I is absent, okay, then the point group may be C infinite V. If the point molecule is linear, which has two or more subsidiary C2s are present, and along with center of symmetry I is also present, that is the point group is C5, okay. It also consisting of C5, then the point group of this molecule is icosahedral. If the C5 is absent, then the point group is octahedral. And if the center of symmetry I is absent, then the point group is tetrahedral. Now, if the subsidiary axes are present, okay, here, yes, subsidiary axes are present, then number of subsidiary axes are present, along with sigma H is also present, then the point group is D infinite H. And if sigma H is absent, okay, and number of sigma D planes are present, then the point group is D and D. And if sigma D is absent, then in case of the point group is Dn. Okay. On the other side, if the subsidiary axes are absent, sigma H is present, okay, then the point group is Cs, okay, and sigma H is absent and I is present, then the point group is Ci, and I is absent, then the point group is C1. Only identity is present. Okay. So on the other side here, in absence of sigma H, okay, no sigma H, then point group is C and H. So sigma H is absent, then and number of sigma V planes are present, then the point group may be C and V. Or no sigma V planes are present and S2 planes are present, improper rotations are present, then the point group is S2N. In case of S2N is absent, then the point group is Cn. So in this way, we can differentiate and to find out the point group of that particular molecule. So all of you clear about this point group? Now time is over, so I will stop over here. A second video. Okay. I will stop over here.